we have to show that the set of all rational numbers is countable. The rational numbers are in the form of a by b, where a and b are integers. If you know the basic topology, or if you know these two concepts, then the result is so simple. It have only two lines. Okay, if you, the first thing is the set of all integers are the countable. Integers are countable. When the integers are in this form, it have positive, negative and zero integers. It is countable, means it has a 1 correspondence between the set of all integers. Okay, and if you know this second term, the second one, countable union of countable sets are countable, then the result has only two sentences. Our set of all rational numbers are the form a by b. We know that a and b are integers. The integers are countable. I am denoting the a by b as a comma b. For understanding our concept easily, I am denoting the a by b as a comma b. Now fixing each term of a, now I am fixing the term a as 0. What become our 0 comma b? 0 comma b have a 1 correspondence between set of all positive integers. I am taking a function like f of 0 comma b equal to b. We know that b is integer and all integers are countable, so it has a 1 correspondence between set of all positive integers, right? This b is countable, so the f of 0 b, it is countable, so the 0b is also countable, so it is countable. Similarly, by fixing each element of a by 1, 2, 3, minus 1, minus 2 and so on, it is all are countable, and we know that the countable union of countable sets are countable, so it is countable. It means that our set of all rational numbers are countable. If you don't know about these two concepts, don't worry, come with me, I will help you to solve this one. We know that the set of all rational numbers are in the form a by b, right? The a by b means it have many terms, like 0, 1 by 0, 2 by 0, 1 by 1, 2 by 1, 3 by 1, 1 by 2, 2 by 2 and so on. It have many terms. And the first thing we need to know that a set is countable only when it can be count the elements like 1, 2, 3. I will give you an example. This set, I am denoting it as A. It have elements x1, x2, x3, x4, xy and so on. If the elements of this set can be counted like 1, 2, 3, 4, 5, 6, 7, okay, then it is countable. The Rudin explained in some more mathematical way. He said that if there is a 1 correspondence between the set of all positive integers and our set, then it is countable set. Look, if I am defining the function like f of I equal to xi, where I belongs to j is the set of all positive integers, then what is f of 1? F of 1 become x1, f of 2 become x2 and so on. So you get the idea. So in the similar way, if we want to say that this a by b means our set of all rational numbers is countable, we can count like 1, 2, 3. Can we count the elements of these rational numbers like 1, 2, 3, 4, 5, 6? You can you think it is impossible, but the question said that the set of all rational numbers is countable. So the first thing we need to do, that we need to make the sequence like this form, okay, to count like 1, 2, 3, 4. So arranging the elements of these rational numbers in this form is our first task. And guys, just look over here. We know that the set of all rational numbers are in the form a by b, where a and b are integers. Is the integers are countable? The integers, like we know that the integers are in the form of -2, -1, 0, 1, 2 and so on. Is this are countable? If this is countable, then we can count the elements like 1, 2, 3. Can we count like this? Let's look on it. I am defining a function like f of n equal to n by 2 if n is even, and f of n equal to -1 minus 1 by 2 if n is odd, where n belongs to j, the set of positive integers. What is f of 1? F of 1 become n is odd. When n is odd, it is minus n minus 1 by 2. For n equal to 1, it become minus, it become 1 minus 1, 0 by 2, right? It become 0. When n equal to 2, it become 2 by 2, 1. When n equal to 3, it become 3 minus 1 by 2, it become minus 1. In similar way, you do, when you do it, you will get like this too. Okay? And so on. This is our integer set, right? So when we can find a 1-1 correspondence between the set of all positive integers and our set, then our set become countable. Okay, we define a function like this, then we get a 1-1 correspondence between the set of all positive integers and our set. It leads that the set of all integers are countable. Now what I am doing is, we know that our a by b, the integers are in the form of a by b. For understanding of the concept easily, I am denoting the a by b as a comma b. Okay, this a by b as a comma b, and I am fixing each term of a with each integer. Then what we get? We get the terms like minus infinity comma b and so on, minus 2 comma b, minus 1 comma b, union 0 comma b, union, and so on, right? 1 comma b, 2 comma b, union, and so on. We get all the integers union, right? Because when we denoting the a by b as a comma b. And firstly I am fixing the number of a as 0. What is 0 comma b become? It become like this term, right? 0 comma 0, 0 comma 1, 0 comma 2, and so on. 0 comma minus 1, 0 comma minus 2 over this side. And this is countable? If this is countable, then we can count the elements like 1, 2, 3, 4. If we can count like this, okay. I am arranging the elements of this set as this form. Okay, 0 comma 0, 0 comma 1, 0 comma minus 1, 0 comma 2, 0 comma minus 2, and so on. If I can find a 1-1 correspondence between the integers and our set 0 comma b, then it is then it has a 1-1 correspondence, right? I am taking f of 0 comma b equal to b, then there has a 1-1 correspondence between these two sets, right? And we already know that the integers have a 1-1 correspondence between the set of all integers. We have shown here, right? We have shown here there is a 1-1 correspondence between the set of all integers and the set of all positive integers. In the similar way, here have two sets, a and the set of all integers has a 1-1 correspondence between the set of all positive integers. We get this related to this and this related to this. Means if a related to b and b related to c, then by equivalence relation a related to c. So this is related to the set of all positive integers, means this can be counted like 1, 2, 3, 4, 5, right? Then this is countable. If we when we take a 0, we get that it is countable. What about when we take a as 1? In this term also, in this similar way, we get that 1 comma b is also countable. What about changing the value of a to 2? The 2 comma b is also countable. What about minus 1 comma b? It is also countable. Minus 2 comma b, it is also countable. In the similar way, at minus infinity comma b is also countable. The infinity comma b is also countable. We get the all terms are countable. Now I am writing the elements in a order way. First I am writing the 0 comma b have elements like this, 1 comma b have elements like this, minus 1 comma b elements like this, 2 comma b, minus 2 comma b, then 3 comma b, minus 3 comma b, etc up to infinity, right? I am taking a sequence in the form in the way of arrow. The first arrow contains the first element of the sequence. The second arrow contains the second element of sequence. The third arrow contains the third element of the sequence. In this way, I am constructing a sequence, right? Now, when I am looking on it, I can find a 1-1 correspondence between the set of our sequence and the set of all positive integers. There is a 1 1 corresponding between 1 and 0 comma 0, 2 and 1 comma 0, 0 comma 1, 3 and minus 1 comma 1 comma 1, 0 comma minus 1, right? We can find a 1 1 correspondence between the set of all positive integers and this set. So we can count the elements in the rational numbers like 1, 2, 3, 4, 5, right? It includes all the elements of the rational numbers. Means it is countable. I will explain it once more. We have to show that the set of rational numbers is countable. So first we said about what is countable set. Then we look the integers are countable. Then we said that fixing each element of A, we get the countable sets, and we know that union of countable sets are countable. By taking a sequence in the form of arrow, we get a 1 1 correspondence between the set of all integers and our set. It shows that our set of all rational numbers is countable.